Welcome back. We're going to talk about the Frank Wolfe algorithm, which is an alternative to projected gradient descent. And the algorithm goes as follows. The main problem is constrained optimization. I want to minimize f of x subject to x in x. What is our usual approach? Oh, and I should also mention in this case I care about f, the setting where f is beta smooth. And we're going to come back to this in just a second. So f is beta smooth. That means that I can run gradient descent. So our usual approach here would be projected gradient descent, which tells me that xt plus 1 is equal to the projection onto x of a gradient step, xt minus eta times the gradient of f of xt. Frank Wolfe does something different. It never will go outside of the set. It'll actually just always stay inside. So Frank Wolfe says, if I'm at xt, let's compute yt, which is the argmin of the gradient of f of xt transpose y, subject to y in x. And then let's let xt plus 1 move along this direction. So xt plus 1 will be 1 minus gamma t times xt, this is where it was previously, plus gamma t times y t. So note that xt plus 1, that at no point do I move outside of the set, and so I don't need to project back in. So yt belongs in x, xt belongs in x, x is convex, so this convex combination that I'm forming in this step is going to remain in the set. So let's see a picture of what this does and why this is different than gradient descent potentially. So first example is just so we can see if we understand if this is making sense. Let's suppose that x is just a sphere. Around the origin. I'm just going to draw the picture here. So suppose that we're at a particular point, and this is my constraint set, and the negative gradient is pointing in a particular direction. So this is the minus the gradient of f of xt. This is my point xt. What direction does Frank Wolfe go in? Is it different than gradient descent? Well, it's telling me to find yt that minimizes the dot product with the gradient. The gradient is I've drawn the negative gradient. So in order to minimize the dot product with the gradient, you'd like to move as far in the opposite direction as possible. In other words, as far in the negative gradient direction. You look here and you see, well, this is a spherical constraint, so clearly this point here that I'm writing would be yt. And so xt plus 1 would actually just be moving me along the gradient. So it looks very simple. Very similar to gradient descent. So this example looks very similar to gradient descent. But let's look at a different example where we don't have a spherical set. And again, this should remind us of all of our discussions of mirror descent, where the geometry of the set, when the geometry of the space, when it stops being spherically symmetric, we may want to do a different algorithm. This is exactly in the same vein here. So let's look at an example that looks a little bit different. So suppose this is my set. And suppose that I'm at a given point here, and so this is my xt, and the gradient is pointing in this direction, the negative gradient. This is a negative gradient of f at xt. So let's think about, where is y going to go? We need to think a little bit about linear programming, but it's pretty simple in this case because we have a set that has flat lines and corners. So where is y going to be? So remember, y is trying to minimize the gradient of f of xt with y. So it's, if you know something about linear programming, you know that the minimization, that the minimum is always assumed at one of the vertices. So in other words, it's going to look at all the corners and decide which is the corner that is the farthest in the minus gradient of f direction, and it's this one. And so in other words, I want to move as much as in this direction as possible, and one way to achieve that is, you can start writing, one way to visualize it is drawing parallel lines that are perpendicular to the gradient. I'll erase these in a second, and see which is the last one. What point does the last line intersect? And the last line will be the one that intersects right at yt. I think this is making this a little bit cluttered, so I'm going to erase these lines, but this is one way to think about what linear programming is trying to do, linear optimization is trying to do. So this is yt. So in short, this shows that the direction that I actually move in is I move from xt in this direction. I drew that arrow long because I wanted to get past what I wrote, the negative gradient, so I'm not necessarily going to take that huge step size, but the point is that Frank Wolfe, in this example, does not necessarily follow the gradient trajectory. It does not follow the gradient trajectory. Okay, so it's in fact doing something quite different. Again, the summary of the algorithm computes the gradient, looks at all of the points in x, all of the extreme points, and it finds the one that solves, that minimizes that linear program over the set, and it moves in that direction. So when is this a good idea? When would we want to do this? So we see that we've taken one complication, projection, and replaced it with another. Because otherwise, the computation is pretty comparable. I still need to compute a gradient, and I still need to add vectors. So the only real difference is that in projected gradient descent, I have this projection step. In Frank Wolfe, I have this minimization step. So let me just summarize that here. In terms of computation, Frank Wolfe replaces projection, which could be a complicated operation, with linear minimization. Linear minimization could also be complicated, but this is just saying that from a computational standpoint, we now have a tool to decide, or we can now select. If we have a problem where the projection problem is complicated, but the linear optimization problem is easy, then there may be a significant win computationally to use Frank Wolfe, and vice versa. So what is the main result? It says as following. Let f and x be convex. Again, my problem here is minimize f of x subject to x in x. And let's further assume that f is beta smooth, but beta smooth in any norm. That's why I put the star on the previous slide. In any arbitrary norm. So in other words, we have that the gradient of f of x minus the gradient of f of y, the norm of that measured in the dual norm, is bounded above by beta times x minus y measured in whatever arbitrary norm we can use. Let's let r equal the diameter of x, in other words, the supremum over all xy in x minus y. Again, note that I'm not using the Euclidean norm. I'm using whatever norm I've used for the definition of beta smoothness. And let me choose gamma t to be 2 over t plus 1. Gamma t is a key part of the Frank Wolfe algorithm. Then, I'll remind you what the Frank Wolfe algorithm here is. The Frank Wolfe algorithm, where I choose yt in the argmin of gradient of f of xt transpose y, and xt plus 1 equals 1 minus gamma t xt plus gamma t yt, this is where we need gamma t, guarantees that f of xt minus f of x star is bounded above by 2 beta r squared divided by t plus 1. So what does this do for us? Well, first we should note that in terms of let me write a capital T just to make this clear. So after t steps, I have this kind of error. So a few comments here. The first one is that just like gradient descent and projected gradient descent, we're not changing the dependence on t. So again, we have order 1 over t convergence, which, as we've said many times, this is the same as saying 1 over epsilon. In other words, if you want epsilon error, the number of iterations of Frank Wolfe, you have to run our order 1 over epsilon. So we're not changing 1 over t. If you look at the lectures on mirror descent, you'll see that there as well, compared to subgradient descent, we were not changing the rate of convergence with respect to the dependence on t. What we were doing is changing the constants. Changing the constants so that they're not defined. There it was Lipschitzness. Lipschitzness was not defined anymore with respect to the Euclidean norm and the Euclidean norm only, but we had flexibility. Here as well, beta is, and this is the point that I've written at the bottom, beta is the smoothness parameter in any norm of choice. And as we've seen a number of times in our segment on mirror descent, trying to convert one norm into another could end up producing dimension-dependent constants. So this could potentially be a significant advantage. And then, of course, there is the difference between the computational requirements, which we discussed on the previous slide. So let's see how this proof works. It's actually not it's not too different from what we've seen already. So one of the key things that we need is this quadratic upper bound in an arbitrary norm. We used the fundamental theorem of calculus to derive the quadratic upper bound for a beta smooth function, beta smooth in an arbitrary norm, in the segment on mirror descent. So if you want to see how that proof goes, you can check out that segment, but otherwise you can take this for granted. So recall that if f is beta smooth. In other words, if the gradient of f of x minus the gradient of f of y, the dual norm, is upper bounded by beta times x minus y, this is again an arbitrary norm, then we have a quadratic upper bound, which says that f of y is less than or equal to f of x plus the gradient of f of x transpose y minus x plus beta over 2 times y minus x squared, again, arbitrary norm. So we're gonna use this. And I'm gonna use this with y equal to xt plus 1 and x equal to xt. So applying this, we've got f of xt plus 1 minus f of xt is upper bounded by the gradient of f of xt dot product with xt plus 1 minus xt plus beta over 2 times xt plus 1 minus xt. Just direct application of what I had above. Now this is less than or equal to gamma t times the gradient of f of xt transpose yt minus xt plus beta over 2 times gamma t squared times r squared. Let's think for a second where this came from. So this just came from the definition of the algorithm. This comes because xt plus 1 is just equal to, let me flip back so you can see exactly what it is. So if you look here, xt plus 1 is 1 minus gamma t times xt plus gamma t times yt. So I've just plugged in for xt plus 1 minus gamma t times xt plus gamma t times yt. Okay, now how about this next inequality? This is less than or equal to gamma t times the gradient of f of xt transpose x star minus xt plus beta over 2 gamma t squared times r squared. This takes a little thought as well. Where did I get this inequality? So the only difference between these last two lines is that yt has turned into an x star. So how has that happened? So for this step, as we mentioned, we used the definition of the Frank Wolfe algorithm. And actually, this also uses the definition of the Frank Wolfe algorithm, but the other part. So this also comes from the definition of the Frank Wolfe algorithm. So let's see exactly what did we swap out. Well, the only thing that's different, I'll write it in a different color here, this term I swapped out the gradient of f of xt transpose yt. I replaced it with gradient of f of xt transpose with some other point, namely x star. So how did I do that and assert that I made things bigger? Well, let's look at the definition of yt. I'll flip back so you can see it in a second, but let me just say it first here. Yt is, by definition, that point which makes the dot product with the gradient as small as possible. And what's x star? X star is just some other point. Maybe it also makes the dot product small, but it doesn't matter because yt, by its definition, is going to have a smaller dot product with a gradient than any other point. So, if instead of gradient of f of xt dot product y, I put gradient of f of xt dot product anything else, I'm only going to make things bigger. And the anything else that I'm going to choose is x star. So this is what allows me to link to the optimal solution. Let's look back for a second to the algorithm just so you can see exactly where this exactly where this comes. And so this is the definition of yt. Yt is that point which minimizes gradient of f of xt with any point in x. Maybe just to be totally clear here, I should write that this is this argument. Okay, so this is this step. So moving on, then this in turn is upper bounded by gamma t times f of x star minus f of xt. This is just our old friend convexity. Right? This is the gradient and dot product with a difference of 2 points. That's going to be upper bounded by f of 0.1 minus f of 0.2. Just the definition of convexity. Plus this term that comes down. Okay, and then you can show that this is putting this all together. We can show that this is the same as saying f of xt plus 1 minus, note what I'm doing here, f of xt plus 1 minus f of x star. The suboptimality is less than or equal to 1 minus gamma t times f of xt minus f of x star plus beta over 2 times gamma t squared r squared. Okay. So this immediately implies this line here. All I did was rearrange terms. It turns out that we're very close. This is basically what we have. So let me copy down what we had from the previous slide. So far, we have that f of xt plus 1 minus f of x star, the suboptimality, is upper bounded by 1 minus gamma t times f of xt minus f of x star plus this other term that I'm carrying around. So this is the suboptimality of xt plus 1. Let me call that delta t plus 1, and by the same token, let me call this delta t. So in other words, delta t is the suboptimality at the tth iteration. So what is it that we want to show? Let's go back to the main theorem. The main theorem is just asking me to show that the suboptimality, this is delta capital T in our new notation, is bounded by 2 beta r squared over t plus 1. So we want to show that delta capital T is upper bounded by 2 beta r squared divided by t plus 1. Okay? And we're going to just prove this by induction. And it's going to be a pretty simple induction because I already have this convenient recursion. So let's assume that it's true. It's easy to check. So check that this is true for t equals 2. For my inductive assumption, my inductive hypothesis, inductive hypothesis, checking that it's true for t equals 2 is just verifying that in the proof that we just gave, we essentially just showed that delta 2 is less than 2 times beta times r squared divided by 3. The inductive hypothesis is that we assume that it's true for all t, and what we have left to do is the inductive step. So we need to show it holds for t plus 1. If you haven't seen a proof by induction before, I'm going over it a little bit quickly, but it's worth for you to review it. The idea of a proof by induction is we want to show that a particular property holds for all t. In this case, I want to show that delta t for any t is less than or equal to this thing on the right-hand side, 2 beta r squared over t plus 1. And the idea for induction is that if you can show that it holds for some base case, in this case t equals 2, and then if you show me the rule for how I go from t to t plus 1, then in principle I've shown that this holds for all t. Because you come along and you say, I don't believe that it holds for t equals 151, but if you believe that I've shown it for t equals 2, and you believe that I've shown you how to go from t to t plus 1, then you just need to apply that derivation, going from t to t plus 1, 149 times in order to get from t equals 2 to t equals 151. So let's show this. So let's show that it holds for t plus 1. Again, this is straightforward computation at this point. So the inequality above here that we've derived and doesn't depend on the induction tells me that delta t plus 1 is less than or equal to 1 minus gamma t delta t plus beta over 2 gamma t squared r squared. And now I'm just going to plug in for what gamma t is and for what my inductive assumption tells me that, that delta t satisfies. So this is less than or equal to, so remember that my choice of gamma t, as stated in the theorem, is 2 over t plus 1. So I've got here 1 minus 2 over t plus 1 times delta t. Delta t is upper bounded by, this is again the inductive hypothesis, 2 beta r squared over t plus 1 plus beta over 2 gamma t squared. This is 2 over t plus 1, this whole thing squared, times r squared. This is equal to t minus 1 over t plus 1 times 2 beta r squared over t plus 1. This is equal to beta over 2 times 4 over t plus 1 squared, or in other words, 2 beta r squared over t plus 1 squared. Collecting terms, this is equal to t minus 1 plus 1 times 2 beta r squared over t plus 1 squared. This is equal to 2 beta r squared over t plus 1 times t over t plus 1. This quantity is less than 1, so I'm only going to make things bigger by dropping it. And this is exactly what we wanted to show. So that completes the proof of Frank Wolfe. Let's end this segment by giving a little example of Frank Wolfe and seeing how it works, and in particular how it works better in some cases than gradient descent. So I'm going to consider minimization of f of x1, x2, x3, subject to a simplex which has corners at 1, 1, but has this huge elongation in the x3 direction. So this is 20. So in other words, this is the point 0, 0, 20. This is the point 1, 1, 0. And this is the point 0, 1, 0. So the simplex, the set that I'm optimizing over is this elongated set. And it's this elongation that's going to be critical. Meanwhile, the function that I'm optimizing is equal to 100 times x1 squared plus x2 squared plus x3 minus 20 squared. So what am I doing? I'm actually putting the optimal solution at this point of elongation. So what is this going to look like? If we just look at, say, the x1, x3 coordinates just so I can draw it a little more easily. And you can think about the simplex as either being, and we could equivalently draw this in 2 dimensions. It will look something like this, where this is the point 0, 20, and this is the point 1, 0. What's happening is that this is the optimal solution, is here. I don't need all these marks inside here. Let's clean it up a little bit. Obviously, this isn't quite drawn to scale. This should be 20, the vertical distance should be 20 times. So this is the optimal solution up at this point. But if we look at what the level sets look like, they're extremely elongated, they're extremely steep. This function is extremely steep in the x1 direction. And so the level sets, let me choose a different color. The level sets look something like this. So what happens when you're out here? Where does gradient descent tell you to go? Gradient descent tells you, I'm exaggerating the length, I'm not saying the step would be this big, of course. Gradient descent tells you to move to the left. But we're going to see that Frank Wolfe is going to tell you from here to move in the direction of one of the corner points. That's what Frank Wolfe does. And which corner point is it going to select? It's obviously not going to move to 0, 0. It's not going to move to 1, 0. It's going to tell you to move directly in this direction. This is the Frank Wolfe direction. Okay? So this is an example where what gradient descent would do is it would move basically all the way to here, and then at some point here start moving upwards towards the optimal solution. So I actually plotted this. So let's see this in action. So this is gradient descent, and this is Frank Wolfe. You can see that the optimal solution is at the point 20, basically 0, 20. I plotted this in 2 dimensions in both examples. And what Frank Wolfe is doing, I don't want to clutter this this figure, but basically this is the set that I drew before. Let me erase that just because it's cluttering it. But you can see that what Frank Wolfe is doing is that Frank Wolfe is essentially almost going in the wrong direction initially, hitting the boundary and then heading north, whereas so that's gradient descent, whereas Frank Wolfe is moving directly towards the optimal solution. And in this example, Frank Wolfe is optimizing much faster with fewer iterations. We'll stop here and we'll pick it up next time.